Get to my spot. Mercy. Okay. This video is going to deal with, this is going to be a summary of the main ideas in the normal distribution. It's going to be a good review for those of you who should know, and for the 1 and 2 people who might be a little rusty or didn't learn it so well, then I hope after this video you're much better at working out the problems and much better at understanding the normal distribution. So without further ado, let's go. The normal distribution is a special PDF for a continuous random variable and is represented by a continuous curve. This continuous curve right here. Okay. It's a special PDF for a continuous random variable. We've been talking for the last couple of videos about discrete random variables. Okay, special PDFs for discrete random variables. Well, this one is for continuous random variable. You would know that a continuous random variable can only take values within a certain range, and so on and so forth. Let's read the specs on the normal distribution. The normal distribution curve has the following features. It's bell-shaped, as you can clearly see there. It is symmetrical about the mean, mu. Mu is the mean. And by the way, because it's symmetrical, the mean, the median, and the mode are all equal. They have the same value. So it's symmetrical about the mean. It extends from minus infinity to plus infinity. Okay. Maximum value of f of x is 1 upon sigma times the root of 2 pi. Okay, showing up at the top here, I guess. Not I guess, I know. Right there. And the total area under the curve is 1. The total area under the curve, the total area under any PDF represents a total probability. And that total area or total probability is 1. No different for the normal distribution. If I want to indicate that a variable has a continuous random variable can be represented by a normal distribution. That's how I write it. X distributed normally with mean mu and sigma squared. Proper way to read that: X satisfies a normal distribution with parameters mu and sigma squared. Parameters are mu and sigma squared. Mu is the mean, sigma squared is the variance. Okay, 95% of the distribution lies within 2 sigma or 2 standard deviations of the mean. That means if I start at the mean and measure a distance of 2 sigma on either side of that mean, put boundaries on either side, then I would be enclosing 95% of the data. Or between those boundaries, I'll have a probability of 0.95. If I extend that, 99.8% of the distribution lies within 3 standard deviations, or 3 sigma, of the mean. Okay. I almost have all of the area under the curve once I've gone 3 standard deviations from the mean. Let's talk about the spread of a normal distribution curve. I have 3 diagrams here showing the normal distribution curve, but even though it's bell-shaped, some of the curves are taller, some are shorter, but you would notice the ones that are taller are also narrower, like the one in the middle, this one right here. It's tall, but it's narrow. That means it has a small variance. Remember, variance measures spread. But once it has a small variance, which means it's narrower, then it has to be taller. The third one, this one here, it's wider, which means it has a larger variance. But the fact that it has a larger variance and it's wider means it has to be shorter. The obvious reason being that you have to maintain a total area under the graph of 1. If the curve gets taller, it can't at the same time get wider, or you would not be maintaining an area of 1. So that kind of makes sense. So for all different values of mu and variance, this second one here, by the way, the mean is 4, the variance is a quarter, as you can see, a small variance. The second one, the mean is 50, displaced further down the line, but the variance is 4, much bigger than the quarter, and therefore that's why you see the wider curve. The first one, and notice I left the first for last, this one right here. This one is referred to as the standard normal distribution curve. And that's probably the most important one you'll be dealing with in this course. The standard normal distribution curve. As you would notice, technically they should have had a Z there instead of X. I'll explain that shortly. So this should have been Z. It is normal 0, 1. Yes. The standard normal distribution curve, what happens is it has a mean of 0 and a variance of 1. Generally speaking, what you will be doing, you'll be converting any normal distribution curve with any mean and any variance into the standard normal distribution curve. Let's look a little closer at the standard normal distribution. I simply repeated what I have up there. It has a mean of 0 and a variance of 1. It's a curve of f of z versus z. And basically, to get from any normal distribution where the variable is x, if x is normal, mu and sigma squared, and you perform this process called standardization, if you standardize x, you end up with z. Z being normal, 0 and 1 squared. Again, you definitely want to do that. You want to convert any normal distribution curve into the standard normal distribution curve. The standardization process is accomplished as follows. To get z, you take x, subtract the mean, and you divide by the standard deviation. That's very straightforward. This means that we can take the PDF of any normal distribution, f of x, and this means that we are taking the PDF of any normal distribution and converting to f of z. Right? We're converting from f of x to f of z. Now, the mathematical function itself, we're not going to do much in this course, but there's a reason I wrote it here, because I'm going to have the pure maths people do a problem for me a little later. What you're doing here is the PDF function on the left, right there, this one here. That is the PDF of the normal distribution curve, f of x versus x, where the mean is mu and the variance is sigma squared. If you replace everywhere you see, if you take x, everywhere you see x minus mu over sigma, you replace it with z, and you replace sigma with 1 and mu with 0, then this function becomes this function. Again, don't worry so much about the mathematics for this course. And the important question should be, why would I want to take any normal distribution that has any mean and any variance and convert it to the standard normal distribution? Why would I want to do that? Well, it has to do with finding the area under that curve. You would remember back when we were doing the generic PDF for a continuous random variable, how did we find the area under the curve? When it was an actual curve, we integrated, right? Well, this function here doesn't lend itself so easily to be integrated. And even if that were the case, it's beyond the scope of this course. Right, the integration that might be required the calculus that might be required to integrate that is definitely beyond the scope of this course. In fact, I've read literature that said that function, it cannot be integrated. So whether it can or cannot be integrated, the mathematics, like I said, or the calculus, doesn't lend itself for this course. So any normal distribution will be converted to the standard normal distribution. This guy. Again, we're not even worrying about the mathematics for the standard normal distribution. What we're going to do is look at the graph for the standard normal distribution. There it is. It's a graph of f of z versus z. Now, if you notice, under that graph, there's a certain portion of the area that's shaded. That shaded portion of area to the left of a Z value, that Z value right there, notice that Z value is a positive Z value. The portion of area to the left of that Z value is referred to as phi of Z. Phi of Z, this notation right up there. Now, because like I was saying before, any normal distribution curve can be converted to the standard normal. Once you've done that, then you will simply look up this table to find those portions of area that would be associated with the probabilities that you're looking for. I have a feeling that some type of numerical technique might have been used to get these areas. And I have a problem, like I said, for the pure maths people that I want them to look at a little later. All right, now let's see how you look up this table. On the x or the horizontal axis is the z-axis, and the area under the curve is phi of z. So for any z value, if I want phi of that z value, I wrote down a couple of examples here. We're going to go through them. Phi of 0.98. You simply look up your table, 0.98. Most of you know this stuff already. 0.98. 0.9, the first column would have the 0.9, and if you go across until you get underneath the 8 directly, there's that value, 0.8365. 0.8365. Now I'm going to look up a z value that has 3 decimal places. Phi of 2.066. So 2.0. 2.06. 2.06 will put me at 0.9808. So did I do that right? 0.9803, sorry. That's 6, yes. 0.9803. This value right here. But I need the third decimal place of 6. So you see the add section all the way to the right of the table, right there. On top gives you the third decimal place. So I'm going to go across in the same row. Go across in the same row until I get directly on the 6. And what it says that I have to add 3. Adding 3 means 3 is the last decimal digit. So adding 3 means really adding 0.0003. So the area to the left of 2.066 is 0.9806. So in there you have your z values in here. These are your z values. And I'm finding the corresponding probability to the left of that z value. And notice that z value is usually a positive z value. On the other side, I'm going to do the reverse. In the brackets, I have the probability. I'm finding the phi inverse function. There. Those are the probabilities in there, which would be in the body of the table, and I have to cross-reference that probability in the body of the table with a specific z value. So let's see, 0.9808. I picked these two values on purpose. 0.9808, I think it's directly in the 0.9808 is this z value right there. Sorry, this probability value right there. What z value is it associated with? 2.07. Right, 2.07. There's the z value right there. In the second case, phi inverse of 0.7600. That value is not directly in the body of the table. 0.7600. So I'm looking in the body of the table for 0.7600. And the closest I find without going over is 0.75, this one right here. 0.7580. excuse me for a second, plus I have to add 20 to get 0.7600. Now let's see if I go across. So 0.7580 right now is associated with a Z value of 0.70. .70, and adding 20. If I go across to the add section, make sure I'm going across in the right row. Go away. Adding 20 means the closest I can add is 18, and that gives me an additional decimal place of 6. So 0.706. And that's the Z value. So you'll need to be able to use the table in both directions, knowing a value of Z, finding a corresponding probability, and then knowing the probability, finding a corresponding Z value. Now, most of the time, don't forget, phi of Z is defined as all the probability to the left of a positive Z value. So in my first diagram, that shaded area there is represented by phi of Z1. Once you can write your expression in terms of phi, you can look up your tables directly for it. Let's look at the second diagram. That area is not to the left of the Z value. That area is actually to the right of the Z value. But that's not a problem, because the area that I'm looking for is the total area on the entire curve, which is 1, minus the unshaded area. And I just found out that the unshaded area was phi of Z1. So this expression would be, for this area here, would be 1 minus phi of Z1. Third diagram. I'm looking for all the area to the left of a negative Z value. In your mind, if you were to flip that curve over, rotate it through 180 degrees, so that the negative Z value appears on the right hand side, you can clearly see that the area to the left of negative Z1 is the same as all the area to the right of positive Z1. And therefore you can write this also as 1 minus phi of Z1. The next diagram shows all the area to the right of a negative Z value. Again, using that concept of flipping the graph around. If you flip it around, you'll see that the shaded area appears on the left, and the negative Z value becomes a positive Z value. So this is just phi of Z1 as well. Next diagram, you want the area between two Z values. Well, if I take all the area to the left of Z2, that would be phi of Z2. If I take all the area to the left of Z1, that would be phi of Z1. If I were to take the difference, that would give me the area trapped between the two. In the next diagram, using that concept of flipping the graph again, rotate it through 180 degrees, Z1 and Z2 would appear on the right, and you have exactly the same amount of area trapped, the same amount of area that you have trapped between minus Z1 and minus Z2. It's the same amount of area that you have trapped between positive Z1 and positive Z2. So this is also phi of Z2 minus phi of Z1. Next, I want the area trapped between, symmetrically trapped between minus Z1 and positive Z1. There are a couple of different ways to do this. This is the way I'm going to do it. Think about it logically. I need the area in the middle, this shaded portion in the middle. That means it's the total area of 1 minus the two unshaded portions. The two unshaded portions are equal in value. Let's look at the unshaded portion to the right of Z1. That unshaded portion is not the same as this one right here. And that was written as 1 minus phi of Z1. So, if I take 1 minus phi of Z1, that will give me the unshaded portion to the right. If I double that, times 2, that will give me the two unshaded portions, one on the left and one on the right. If I take those unshaded regions away from 1 minus that, then that will give me the shaded portion in the middle. Seems logical. Let's simplify this. Open up the brackets. 1 minus 2 plus 2 phi of Z1. So this ends up being 2 phi of Z1 minus 1. Next. Well, I want the two unshaded portions on the left and right. Well, I just figured out that I want the two shaded portions on the left and the right. The one to the right, I just figured out it's 1 minus phi of Z1. And if I double it, 2 times that, then that will give me the two shaded portions, one on the left, one on the right. Okay, that's easy enough. The last one I have here, I need the shaded region between, and it's not symmetrical. The shaded portion to the right, the unshaded portion to the right can be written as 1 minus phi of Z1. The unshaded portion to the left can be written as 1 minus phi of Z2. If I add them, so this plus this, and then subtract all of that from 1, I'll get this piece in the middle. I'll get the portion shaded in between. Let's tidy up. This is 1 minus into, that's 1 and 1, that's 2. Minus phi of Z1 minus another phi of Z1 minus 2 phi of Z1. I push the minus inside. 1 minus 2 is, I messed this up. Let's do this again, this portion. Everything above is correct. This is 1 minus into 1 and 1 is 2. This is minus phi of Z2. This is also minus phi of Z1. Two different portions. 1 minus 2. Okay, why am I getting a negative? Let's try this again. This entire thing. My logic seems messed up. I want the shaded region in the middle, or in between those two lines. 1 minus phi of Z1 is that portion to the right. Plus 1 minus phi of Z2 is that portion to the right. If I take 1 and subtract that, 1 minus this, shouldn't that give me what I'm looking for? So this is 1 minus 1, that disappears. This becomes phi of Z1. That becomes plus phi of Z2. And that becomes minus 1. Yeah, that looks good. I don't know what happens to my math sometimes. Z1. Good. All right, so once you can rewrite your expressions in terms of phi, you look up your tables and find your expression in terms of, find the value for phi of whatever z value. Okay. All right, let's keep moving. What do I have here? I have my first problem that I want to go through. Now, like I said, because this is a summary, I'm only going to go through 2 problems. And then I have a little worksheet at the end for you to work on. It only has like about 5 or 6 problems, I think. All right, so let's check it out. The number of hours of life of a torch battery is normally distributed with a mean of 150 hours and a standard deviation of 12 hours. One of the things you should always get accustomed to doing is writing out in words your random variable. What it is, x is a continuous random variable, CRV, that represents the number of hours of life of a torch battery. Okay. They told us that x is normally distributed and the parameters are it has a mean of 150 hours and a standard deviation of 12 hours. Now remember, the parameters are really the mean and the variance being the square of the standard deviation. Good. In a quality control test, 2 batteries are chosen at random from a batch. If both batteries have a life less than 120 hours, the batch is rejected. Find the probability that the batch is rejected. Well, what we're going to do up front, we're going to work on one battery and figure out the probability that that one battery, any one battery, can last for less than 120 hours. And then see what we have to do to account for the 2 batteries. So let's find the probability. Find the probability that x is less than 120. You will not be able to look up an x variable to find probabilities, which means you have to standardize x. Remember how you standardize x? If you standardize, you get, this becomes the probability that x minus the mean, which is 150, upon the standard deviation, which is 12, must be less than the specific value of x, which is 120, minus the mean, which is 150, upon the standard deviation of 12. So when you standardize, this becomes the probability of x minus the mean over the standard deviation, that's z. And we're looking for the probability that z is less than 120 minus 150. I think that's minus 30. And you divide that by 12. Minus 2.5. Z is less than minus 2.5. How do you find that probability? Okay, well, let's see. You want to drop the standard normal distribution curve. Let me not freehand this. Standard standard normal distribution curve. Just gotta find the curve itself. And this is f of z versus z. This is 0. The mean is 0, remember. I'm looking for the probability that z is less than minus 2.5. Minus 2.5 is somewhere over here. So I'm looking for that area over there that I just shaded, which would represent the probability that z is less than minus 2.5. Well, we just went through a whole list of scenarios. Let me see which one that would satisfy. If I remember correctly, I think it's the second one. No, the third one. There. You're looking at the probability that you're less than a negative z value. That's 1 minus the probability that you're less than the positive z value. 1 minus phi of 2.5. If I go up to my normal distribution table, 2.5. 2.5. That would be 0.9938. 2.50, that would be, yes. 0.9938. One minus 0.9938, which gives me 0.0062. So let me just summarize that portion right there. What I've just found is that for any one battery, the probability that X is less than 120 hours is equivalent to saying the probability that Z is less than minus 2.5. And we found our probability to be 0.0062. One battery. But a batch will only be rejected if 2 batteries end up having a lifetime less than 120. And the batteries are independent. So the probability that the first battery has a lifetime less than 120 hours is 0.0062. Probability that the second battery has a lifetime less than 120 hours is the same, 0.0062. How do I find the probability that both batteries, the first one and the second one, they both have a lifetime less than 120 hours? You multiply. When two events are independent, to get the overall probability, you multiply. So the probability that both batteries have a lifetime less than 120 hours is equal to 0.0062 all squared. Which is tiny 0.0000384. 0.0000384. 3 significant figures. And the probability that both batteries have a lifetime less than 120 is the same as saying the probability that the batch will be rejected. So this is also the probability that the batch is rejected. Quality control, all right. Same probability. All right. Let's take a look at the second problem. This comes from exercise 70 on page 381, number 8. Metal rods are produced by a machine having lengths that are normally distributed. So let's see how best we can define our our random variable. X is a continuous random variable that represents the lengths of metal rods produced by a machine Okay. Now they didn't give you the mean and the variance. In fact, in the body of the problem, they want you to find the mean and the variance. This is an interesting problem. So we'll start by saying x is normally distributed with a mean of mu, which we don't know, and a variance of sigma squared. Okay. I'm going to start by drawing. Let's try again. There. Okay. I'm going to draw the original f of x versus x normal distribution curve. F of x versus x. The mean, we don't know, it's mu. The variance is sigma squared. Okay, now they said 2% of the rods are rejected for being too short. So there is some length over here. I'm going to call it L1. There's some length L1 such that if the length is less than that, it's going to be rejected. The probability of that, which means the area under the curve for that portion, is 0.02. And they also said that 5% are rejected for being too long. There's a length over on the other side where this area or region is 5%, 0.05, and this length is L2. Actually, I just realized in the body of the problem they told you what the lengths are that are the acceptable lengths. The least and greatest acceptable length is 6.32. So this L1 is actually the 6.32. And this L2 is 7.52. Okay. Calculate the mean and variance of the lengths of the rods. So they basically gave me two bits of information, which I'm going to translate into probabilities. The first one will say the probability that x is less than 6.32 is 0.02. And on the other side, I'll say the probability that x is greater than 7.52. That's equal to 0.05. I'll standardize both sides. The probability that x minus mu over sigma is less than 6.32 minus mu over sigma. That's equal to 0.02. And then I'll draw the f of z versus z graph, the standardized graph for this guy. This is f of z versus z. Now, this value here is going to end up being some specific value of z, which I'm going to refer to as z1. This is just a generic variable representing z. So I'm going to rewrite that as the probability that z is less than. Now the only way, if I go less than, I can get a probability of 0.02. If I start here, less than means I'm shading over to my left. So that's actually a minus z1. So the probability that z is less than minus z1 is equal to 0.02. Less than negative Z1 is the same as greater than. This is the same as the probability that Z is greater than a positive Z1. That's 0.02. And that's the same as 1 minus the probability that Z is less than Z1. That's 0.02. 1 minus, this can be written as phi of Z1 is 0.02, which makes phi of Z1 as the subject 1 minus 0.02, which is 0.98. And therefore Z1, if I make Z1 the subject, Z1 is phi inverse of 0.98. Remember how we did that up front? Let's see if we can find that value in the body of the table. 0.98. I'm looking for a probability of 0.98 in the middle. 0.98. I'm not going to find that directly. The closest one is 0.9783. That means I have to add 17. Is there an add 17? 0.9778. 0.9778. .9783, sorry. Jeez. 0.9788. That's the closest. No, finally, 0.9798 is the closest. The next one is 0.9803. 0.9798, which means that's an add 2. All right, so I'm looking at 2.0, 9798, 2.05, 2.05. Jeez, I'm slow on the blocks here, man. 2.054. 2.054. Now, if we were to go back and associate this negative Z1 value with this guy, we get an equation relating mu and sigma. 6.32 minus mu over sigma is equal to minus Z1, and therefore 6.32 minus mu is equal to minus Z1 times sigma, or 6.32 minus mu is equal to negative 2.054 times sigma. That's one equation in two unknowns, mu and sigma. Hope my algebra there is right. We're going to go to the second one and do something similar. We're going to standardize first. So this becomes the probability that x minus mu over sigma is greater than 7.52 minus mu over sigma is equal to 0.05. The error would still remain the same even if you standardize. Okay, if we were to graph that as an f of z versus z graph as well. Can I steal this one? Oh, forget it. Draw it over. Okay. All right, you're shading greater than. The only way you can get greater than with such a small probability If you have a positive, I'll call this a Z2 value. So if you want to rewrite that expression, it'll look like the probability that Z is greater than a positive Z2 is equal to 0.05. So this becomes 1 minus 5Z2 is equal to 0.05. 5Z2 is equal to 0.95. Z2 is equal to phi inverse of 0.95. Lookup tables, part that I hate. Phi inverse of 0.95. 0.9495. So let's add 5. So first we're looking at 1.64. 1.64. So add 5 means the last decimal place is a 5. 1.645. Z1 is 1.645. And again, what we'll do is relate that Z1 value we just found Z2, sorry, not Z1. Yes, remember we had a direct relationship between these two? So Z2 is equal to 7.52. So 7.52 minus mu over sigma is Z2, but we just found Z2 to be 1.645. So 7.52 minus mu is sigma times Z2. 7.52 minus mu is equal to 1.645 times sigma. That's the second equation. Two equations and two unknowns. If you solve them simultaneously, you get both mu and sigma. So let's see. I want to go through it, make sure my numbers were correct. I lay them side by side. I'll write the second one first. Sure. Yeah, let's go. 7.52 minus mu is equal to 1.645 sigma, and the first one is 6.32 minus mu is equal to minus 2.054 sigma. I will subtract the two equations. That's 1.2 minus mu disappears, and minus gives you a plus on the other side. So this is 1.645 plus 2. And therefore sigma would be 1.2 divided by 3.699. 0.324. 0.324. And now that I have sigma, I can go back and find mu. Just take sigma and plug it into either one. Let's see, for the first one, make mu the subject. Mu would have been 7.52 minus 1.645 sigma, which is 7.52 minus 1.645 times 0.324 mu. That will give me 6.96. I'll take that. If I'd used the full value, let's see what I would have gotten. Divided by 3.699. 0.3244, 3.32, then times this would have been 6.99 if I had used the full value for sigma. 6.99. So I can now write my distribution is x is normal 6.99 and 0.324 squared. Not too bad. That's summary for most of y'all. The second part of the problem, what is that asking for? If 10 rods are chosen at random from the batch produced by the machine, find the probability that exactly 3 of them are rejected for being too long. Well, the probability of being rejected for being too long is 0.05. Probability of being rejected for being too long is 0.05. That any one rod is rejected for being too long. That p-value is 0.05. The length, we already know what the length would have been. The length that you have to have for being rejected for being too long is 7.52 centimeters. And the probability of being rejected for being too long is 0.05. Okay. Now 10 rods are selected. We want the probability that exactly 3 are being rejected for being rejected for being too long. See the connection? I see a binomial distribution right here. Right? There are 10 trials, 10 rods. All the trials are independent. What happens with one rod? The fact that one rod can be rejected for being too long has nothing to do with the other rods. Probability of a success being the rod is rejected for being too long, is the same for all the rods, 0.05. And what's the fourth condition again? Independent, finite number trials. Probability is the same for all. What's the fourth one? Man, my brain. I am not stopping until I find it. Independent, p-value is the same for all finite number trials. Yes, 2 possible outcomes for any one trial. You either are too long or you're not too long. So it's clearly a binomial distribution here. x, I'll call it y, new variable. Y now is a discrete random variable. See how some of these problems morph from one distribution into the other? Y is a discrete random variable that represents the number of rods that are rejected for being too long. Out of 10 rods, we know the probability of any one rod being rejected for being too long, and we know the number of rods we're dealing with. So therefore, y must be binomial with parameters 10 and 0.05, which means the PDF would be probability x equal x would be 10cx times 0.05 to the power x, 0.95 to the power 10 minus x. How do you like them apples? And we want the probability that exactly 3 are being rejected for being too long. Probability that x is equal to 3 would be 10c3 times 0.05 to the 3 times 0.95 to the 7. Let's check that number out. 10c3 is 120. I know that number by heart. Times 0.05 times 0.0105 0.0105, and that's that probability. I'm gonna bring this video to a close because I think I've accomplished what I wanted to. You have a nice little worksheet at the end here, and that will give you good revision. I didn't assign a lot, total of 4, but I made sure I chose the tougher ones. So for the review people, you have something to make you think a little bit. All right, that's it for this video. I'm out.